I'd like to introduce our speaker this evening, Dr. Emma Chapman. It's particularly pertinent, I think, because today is Ada Lovelace Day, a great woman scientist who invented the first computer. Now, Dr. Chapman is Royal Astronomical Society Research Fellow here at Imperial College. She was awarded a first-class master's at Durham before coming to London to complete a doctorate at University College on seeing the light. She's won a number of awards, including the UCL's Chris Skinner Department of Physics and Astronomy Thesis Prize for her work, and also the Institute of Physics Early Career Woman Physicist of the Year, awarded in 2014. She's highly commended in the 2017 L'Oreal UNESCO Woman in Science Awards. I like to say that with so many women and young women in the audience this evening, I particularly like to say that this is another area of her commitment to scientific research. She's worked to ensure the problem of bullying and harassment within STEM subjects is taken seriously and works to improve the workplace culture at universities. She was awarded the Royal Society Athena Prize for her work to end staff-student sexual harassment and bullying in academia. And she's a leading member of a group called the 1752 Group, and was the 2018 recipient of the Royal Society Athena Prize for driving nationally impactful policy changes concerning sexual harassment in higher education. She's also about to publish her first book, First Light. Emma, I'd like you to welcome Emma Chapman.
Thank you very much. That was a very comprehensive introduction. I'm Emma. I work here at Imperial College London in the Astrophysics department. As of last week, I'm a Royal Society Dorothy Hodgkin Fellow, a very recent thing. I've been here for about 3 years, so I'm very pleased to be able to talk to you about the kind of research that I carry out here. So you may have noticed there's quite a lot of me at the minute. Don't be alarmed, I have 5 whole weeks left, so hopefully we'll all be fine. But what this can really serve as a very visual reminder of during this talk is why knowing about the first or the beginning of something can really help us understand a lot more of the context, the wider context. So when you look at me, hopefully you're not alarmed. Hopefully you're not weirded out, because you have a lot of data about what this means. You understand that there is a new life forming, and that new life, or how I am now, fits into, for example, my chosen life pathway. But what if you didn't have all of that data? So what if we're aliens in Andromeda, for example, observing Earth, and how do they know what I am in terms of the life cycle of a human? Well, that will all depend on how they take their data. So if our alien is overworked or on a minimal research grant, then they will probably not have that long to actually observe the human race. They won't be able to sit there for 100 years and watch a lifetime. What they will do is instead they will take a sample. So they will look at different areas of Earth, and they will try and take snapshots of the different types of human and try and fit them all into an understanding of what's going on. But if they're taking their samples incorrectly and completely, for example, let's say our alien just happens to look at Alton Towers on a Tuesday, then they might miss several parts of the human life cycle. When you have incomplete data, it's very, very easy to make incorrect conclusions. It's not that far-fetched to see how, if you observe, certain environments, then that alien might come to the conclusion that actually, certainly in Alton Towers, this kid's talking about a stork. Everything's right, everything's perfect, so let's write up the grant and we're done. So what is vital to do when we're actually researching something unknown is to make sure that our data is complete. So what our alien in Andromeda need to do is they need to take a complete snapshot. They need to look at lots of different environments. They need to look at lots of different times in that universe. And that way, you start to get a complete lifetime. Now, as astronomers, that's what we do with our universe. So we look at lots of different environments. We look at the Milky Way. We look at other galaxies. We look at stars when they're just forming. We look at galaxies when they're just ending. We look at our own sun a lot because it's very close by. In doing that, we can actually build up a life cycle of a star, for example. So we can see a supernova and we can start to understand that that fits into the life cycle of the star as the end of the star. We can see black holes and we can understand that that is also another end of a star's lifetime. But what do we do when we're trying to understand the lifetime of a universe? Because with the universe, we can't just look at different universes. We can't take a snapshot of lots of different universes at lots of different times in that universe's life and try and fit them together into a pathway. To actually understand the lifetime of our universe, we need to be a lot more clever. So here we've got a lifetime of our universe from 13.6 billion years to the Big Bang, for example. But you might notice I'm going quite slow. I'm very short of breath. So you have to bear with me if I'm breathing a bit funny. Right. So when we're actually looking at this universe, we want to start by we need to extrapolate the data we do have, because we can't make samples from different types of universes at the moment. So one of the things that we have managed to extrapolate backwards to is the Big Bang. So hopefully everybody in this room has heard of the Big Bang. It's the theory that the universe started from a single infinitely dense point and very rapidly exploded and inflated and expanded into the universe that we see today. Now, we came up with this theory not by looking at the universe and seeing a Big Bang, but by seeing its after effects, by seeing the effects of that Big Bang. So we observed that the galaxies that we... is there a pointer? Here's a pointer. Sorry. Yeah. So we observed that the galaxies that we could see all around us, all around the Milky Way, the vast majority of them all seem to be travelling away from us. And that's exactly what you would expect in an explosion. So just like if you're watching an action movie and you see Arnold Schwarzenegger flying one way and Bruce Willis flying another way, and I don't know, one of the others flying the other way, then you can extrapolate backwards and you know that at some point they were all roughly in the same space and exploded outwards. So when we looked at these galaxies expanding like that, exploding like that, we knew that at some point all of that matter had to have been roughly in the same place. And more than that, actually, when you think about that action movie, you always see the heat, you always see the fire, the energy coming from these explosions. And it's exactly the same with the Big Bang. So people theorised that there would be this afterglow of radiation emanating from the Big Bang. And indeed, they did in fact detect it at around 1965, called the cosmic microwave background. It's a map of it there. That's actually, it's all around us, it's a full sky map, it's just we've flattened it. Now, we're very happy with ourselves because we understand something so incredible. 13.6 billion years ago, we think we know how the universe started. But what happened afterwards? Well, we can use our mathematics, we can use our thermodynamics to understand that a very early universe is very, very hot. It's very, very energetic. There's not much that can hang around apart from hydrogen and helium. It's very small atoms. And that's because it's like having, it's like a nursery, trying to build a Lego tower in a nursery full of 30 hyperactive, sugar-crazed children. You can try as you like to try and build bigger and bigger blocks, but at some point, very shortly, one of them will just knock it straight down. And so we have to wait. We have to wait until that universe is expanded, until it's cooled, until we can start to build bigger and bigger molecules, or atoms. And it turns out that actually, even when the universe is expanded quite a lot, we can only ever really create hydrogen, helium, tiny bit of lithium. So this is a big mystery for us, because we were very proud of ourselves for understanding the Big Bang. We're very proud of ourselves for being able to observe, say, galaxies nearby all flinging themselves away from us. But what on earth happened in between? How did we get all of these heavier elements? As humans, we tend to like to collect things. And if we look at the periodic table, when we take the biggest theory in cosmology, the Big Bang theory, then what we're accounting for is these three. And that's it. So we're not very happy with ourselves in terms of our collection. So how do we get everything else? Now, as a side note, during this talk, I'll be talking a lot about metals and metal-free stars. The astronomers have a very different type of periodic table to the chemists and anybody else, basically. Whereas chemists will name every single element, we are so used to just dealing with hydrogen and helium that we have hydrogen, helium, and then metals. So absolutely everything else we call a metal, genuinely, not even just for shorthand. So when I say metal-free, I mean that it's just hydrogen and helium. When I say that it's metal full, or whatever I say, then I mean it could be anything beyond hydrogen and helium. And I'm sure there are some chemists in the audience, and I apologise, but this is just the way I've been brought up. Let's see if this plays.
Do you want the lights down a bit more?
If possible, yeah, actually. That would be good. Just trying to see if that is playing. Okay, excellent. You may be familiar with this video already. This is the Hubble Ultra Deep Field. This is genuine data. So this is not a simulation, as is very cliche to say, but this is true. This is taken on an area of the sky around a fifth of the size of the full moon. And these are all galaxies. Very nearby galaxies. And I find it absolutely fascinating just to see the diversity and the complexity of the structures actually in our universe. So how on earth did we get from just hydrogen and just helium to that? When we look at our understanding of our universe, Hubble and other kind of other observations takes us back to around here, like a few billion years ago. The Big Bang is obviously right at the beginning, and we theoretically know what happened, but we've got the cosmic microwave background at least. But in terms of what happened in between, we actually have about a billion-year gap in our knowledge. So that's a billion years in the lifetime of our universe that as scientists, we really have no data. We have no direct or even indirect observations of that time. That's quite a large number to not understand. So what's happening? We are missing all of the first stars. We're missing all of the first galaxies and all of the black holes. We're seeing the second, the third, the fourth, the fifth, the umpteenth generation of all of these entities. But why do we care about the first? Does it really matter? Well, as I've already said, having complete data sets, understanding the first of something can actually lead us to understand the last of something very well. Having an incomplete data set can lead to incorrect conclusions. So already we want to know about this. But more than that, the first stars are actually incredible entities in their own right, because they evolve in a universe that's completely different to the universe that we live in today. So for a start, because they're only forming out of hydrogen and helium, these very first metal-free stars, we think they were incredibly large. So we think that they were around 100 times the size of our sun, which is very, very big indeed. There are stars like that exist these days, but these would have been the only stars in the universe, these incredible beasts of things. And when we run simulations about how these stars formed, it's all to do with the fact that they did grow up in a very pristine universe. Just this hydrogen, just this helium. Because of that, they couldn't cool down efficiently, and they got really, 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 really large. And when a star is really, 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 really large, it dies very, very, very quickly, because it eats all of its fuel up very, very quickly. And so this is a simulation of some of the first stars. On the left, you just saw a supernova. I think you're about to see another supernova from memory. We know that these first stars, there we go, lived very short lifetimes. So if you were talking about a human as a normal star, like our sun, say 10 billion years lifetime, then a first star like this would live 3 days in comparison. So we're talking a few million, 100 million, tens of millions of years, and that's it. And when they died in incredible explosions called pair instability supernovae, which utterly obliterated everything around them. So because they obliterated their own environments, they prevented other first stars from forming. And that's why we only ever see them in 1s or 2s or 3s. We certainly don't see these giant clusters of stars like we see in the Milky Way today, for example. But what they did when they did explode was they seeded the entire universe with metals. Because as they burnt through their hydrogen, as they burnt through their helium, they would start to form heavier and heavier metals. So it's like they were acting as a nuclear reactor. And when they exploded, that energy just got even more, and they could even make even heavier metals and start seeding the universe, ready for the next generation of stars like we might see today. And I think this is a really incredible picture of, you've waited 400 million years after the Big Bang. Everything's dark. Everything's very empty by visible light, certainly. And then suddenly, one by one, you have the whole universe just light up. All of these first stars turning on for the first time like twinkle lights in the sky. And as they do that, they evolve, they seed the second generation, and you start to get the galaxies. And they're forming from all of this gas that's just lying around after the Big Bang, which is what all of that diffuse blue stuff was. Now, it's a wonderful picture, this idea of them starting for the first time. But we don't have any data on it. We've never actually observed this time. This is all from theory. And indeed, it's easy enough for us to go backwards and say, well, clearly we've got very metallic stars now. We know the universe was metal-free. Something had to have come in between. What was it? But we've been searching them for so long that even in 1981, people were publishing papers saying, where is population 3, which is the terminology for these first stars, population 3 stars, where our sun is population 2, for example. So why can't we find them? Well, firstly, they could be hiding. So the universe was very pristine, as I've said, just hydrogen, just helium, when they were formed. And so we've been looking in our own backyard, we've been looking in the Milky Way for very metal-free, pristine stars. And we haven't found any. But of course, the universe has changed dramatically since these stars were born around 13 billion years ago. We no longer live in a nice, clean universe. We live in a very dirty, polluted metal universe. And so it's quite plausible that actually these first stars are there, but they have been hidden by a whole load of metal pollution, as it were. They're camouflaged, and so maybe we're looking for the wrong thing. And what we need to do instead is start looking at these low metallicity stars in the Milky Way, for example, and figure out ways of scraping off that metal, scraping off the dirt, if you will, within the data, and revealing whether these are actual genuine artifacts. This is called stellar archaeology. It's something that a few people are putting a lot of work into doing in terms of discovering the very, very first stars, in the hope that they will just find one floating around in the Milky Way, basically, that has been around for 13 billion years, happily alive. But of course, I've already mentioned that most of our simulations are showing that these stars were very massive and lived very short lifetimes. So when we actually look at a figure of how long stars live, so this one solar mass is our sun, 60 solar masses is a star that's 60 times the size of our sun in terms of mass, and then you've got the life expectancy here. So when we're looking for the first stars, we need these stars to have survived for about 13 billion years. And if you look at that graph, 13 billion years, which is where the red and the blue intersect, is maybe the size of our sun or less. And that doesn't fit with any of our models. So the possibility that's gained most traction recently is that actually we're not finding them because they're all dead. They're all long, long, long gone. They all died billions and millions of years ago. Sad. Except, luckily for us in astronomy, just because something is dead doesn't mean we can't still find it in a very, very spectacular way. So not just in a way of finding the fossils like you might for, if you're a paleontologist, but we actually have the opportunity to see these first stars again using some very exciting properties of light. Because when we observe our universe, we tend to use light. And light has a very finite speed. So it's about 3 followed by 8 zeros meters per second. It's extremely, extremely fast, light. And the reason we don't notice that it is so fast, so for example, if I wave at you, you see it instantaneously because the light from my hand is reaching you in such an incredibly quick time that we can't even register the delay. So when we look through our telescope at our neighbour, for example, watching Great British Bake Off, you can see that programme at the same time as it's on your TV for the same reason. But when we look at the nearest star, that light has had to travel over a much further distance. And so there'll be a bit of a time delay between an event happening on that star and us observing it. And when we get to even galaxies further away, then we'll see an even greater delay. Now, this is something that's very easy to register when we're looking at our universe. So we see the sun, you might have heard this fact a lot, that when we see something happen on the sun, for example a flare, then we know it happened roughly 8 minutes ago because of the distance between the Earth and the sun. When we look at Mars, we're looking at light 3 minutes ago. Alpha Centauri, our closest star, 4 years, and Andromeda about 2.5 million years it takes light to get to us. So we are seeing Andromeda 2.5 million years ago. So it doesn't take much to see how we're going to see these first stars. If the further we have to look with our telescopes actually means we're looking back in time, then we just have to build a telescope that can look so far away that it's taken 13 billion years for that light to reach us. And that's exactly what we're going to do. So this isn't us finding a fossil of a first star. This is us building a telescope which can look back in time, which can look at these first stars 13 billion years ago and draw direct conclusions, draw direct samples, and complete our understanding of the universe. See, something I find fascinating about all of this is that, with our alien in Andromeda, for example, that was a completely false story, not just because, who has the time to be looking at Alton Towers, but because actually this alien wouldn't even be able to see the human race for another 2.5 million years from now. Actually, if there is an alien on Andromeda right now observing Earth, they are seeing the very first emergence of the Homo genus. So they are seeing this chap here, which I find incredible. And it's the same as if I was to build a telescope here and through some clever optics look at Egypt, and I would be able to see them building the Great Pyramid. And I would be able to do that. That breaks no laws of physics as long as the speed of light was low enough. That's exactly what we're doing in space. Now, there's one more complication. There's quite a few more complications, actually. But the major complication is that it's not as simple as just building a telescope that can look that far back and be able to see that very first little star. Instead, we're nowhere near that, technologically speaking. It's like having a camera with all these different zooms, and we're only in the top left, where you can just about see the little red house if you look very, very hard. But we can't really get much further than that at the minute. So how can we hope to see these first stars if our telescopes aren't good enough? What we're going to do instead is we're going to look for their effect on the environment. So instead of looking for an image of the very first star, which is very, very tiny, 13 billion years away. I don't know if you've ever seen that Father Ted sketch with the cow that's farther away and close. You know, it's very, very difficult to see something that small that far away. But imagine that house, for example, was pumping out a huge coal fire. Then with whatever zoom camera you have, you can actually see the effect of that on the environment. You can see these large coal clouds, for example. And from that, you can draw conclusions and say, right, well, clearly we can see this big cloud. There's human habitation of some kind, for example. And that's exactly what we're going to be doing with our universe. We're going to be looking for the evidence of these first stars, just like, you know, mice are very difficult to see. We're going to see them nibble the Swiss cheese, as it were, and see the evidence of that. So let's look at this video again and not just wonder at how pretty it is, but look at what effect these stars are having on their environment. So about 400 million years after the Big Bang, you've got these massive clouds of hydrogen and helium. And as these first stars come to life, then you'll notice not only are they evolving in their own right into second generations and galaxies, but they're also doing something very interesting to the hydrogen. They're burning it away. So they're actually doing something called ionizing it. They are knocking the electrons away from the protons that make up the hydrogen, so that there's just no hydrogen left. And this is what we're going to use as a tracer. So instead of looking for the very first stars themselves, we're instead going to look at how they have an effect on this hydrogen, because that's much easier to do. Because they burn away this hydrogen in very easy fashion to follow mathematically, I suppose. They blow bubbles. So in the lifetime of our universe, we can start filling in our blanks by saying, well, we know that these stars actually blew bubbles within this hydrogen. They burnt holes. So it's just like holding a lighter up to a piece of paper, really, and it burning a hole in it. It's the same kind of thing. We're looking for a cosmic Swiss cheese, as we call it. It actually is called the Swiss cheese model. And it might seem quite underwhelming that we're just looking suddenly for very giant bubbles. But actually these bubbles can tell us a huge amount. So the way that the first stars will ionize this hydrogen is by blowing or burning incredibly neat spherical bubbles. So that is the Swiss cheese model, because it really does look like a piece of Swiss cheese when you look at the hydrogen. But if you're instead looking at one of the first galaxies or first black holes at the centre of the first galaxy, then what they do is that they ionize the hydrogen in a much more violent, fast, wispy, big effect. And so you get these massive, wispy, big bubbles in comparison. So it's not just that we can see a bubble and say, right, there's something there. It's that we can see a bubble and we can try and infer from below it what's behind. So this is much more what we'd observe. A whole sea of hydrogen with holes in. Quite underwhelming. But the science we can get from that leads us back to a huge amount of knowledge about those first stars, which quite frankly has to do when we haven't got the technology to look back 13 billion years to see those teeny little things. And we can do this over time. So we can look not only a distance where the light's 13 billion years old, but we can also tune our telescope to look a little bit closer. And we see those bubbles start to grow and grow, because as more radiation is pushed out from these stars, it burns bigger and bigger holes. These bubbles get bigger and bigger until eventually, about 1 billion years after the Big Bang, there's no hydrogen left. It's all gone. And the way that we are going to observe this is via radio. Hydrogen, you know, we've got hydrogen in this room. Me saying, oh, we're going to build a telescope and take a picture of this hydrogen doesn't really mean much, because I could take a picture now, I couldn't show you the hydrogen with it. But luckily for us, hydrogen produces radiation which by the time it gets to us is in radio waves. And radio is just another kind of light, which is very, very convenient for us. So we might be very used to, I'm not sure the levels in the audience, but we might be very used to hearing light and thinking optical, because that's the part of the electromagnetic spectrum that our eyes are evolved to observe. So, this is where we think of light. But actually light is this whole massive spectrum of different wavelengths of photons. Where if you have extremely energetic light, then you're looking at something like gamma rays, you're looking at something like X-rays. If you're observing something much lower energy light, then instead you've gone into your radio, you've gone into your microwaves. So observing something in radio is not like listening, it's just like seeing, but a different energy of light. And using different types of light is the bread and butter of astronomy, because it can reveal whole different things about your universe. It's like going to the doctor with a suspected broken wrist. You'd be pretty annoyed if they just looked at it under a lamp and said, probably broken. You'd want them to look at it with an X-ray. It's a different kind of light. It gives you a different kind of data. And that's what we do in astronomy. So, for example, this is Centaurus A. The galaxy is observed with an optical telescope. Looks all very nice and everything like that. But then if we look at it actually observed with a lot of other different types of light, mainly your UV, most importantly your X-ray and your radio, then you can see these incredible lobes form. And that's because the plasma that's creating those lobes coming out of the galaxy only produces radio light. It doesn't produce low enough energy for us to see optically. And on the right there's a composite image of it all together. So you can really see how the different types of light add a lot of different types of information. For example, before we looked at Centaurus A just in the optical, it looked like a very standard galaxy. With our radio data, suddenly we understand that there is a gigantic black hole in there that's pushing out all of this plasma. So hopefully I've convinced you that radio is a sensible thing to observe in, even if it's not as intuitively pretty. So how are we going to do this? Well, luckily radio telescopes are not new. They're actually very old, and they are basically based on the same technology as you will have had on your car, if you're old enough to remember the antennas. And you know that basically the bigger the antenna, the better the signal. So if you want to hear your local radio station, you can get away with your car antenna. If you want to hear a radio station in China, then you have to have one heck of a dish or an antenna. So to look back 13 billion years, we're going to need a pretty darn big radio telescope. So this is one of the biggest antennas that we had in November 15th, 1988. We need something bigger than that, except that this is the Green Bank telescope on November 16th, 1988. Not so good. It was very big, but it couldn't work for very long. And because it developed a massive structural engineering issue. That's an understatement there. So we can't just build a bigger and bigger and bigger telescope in order to look back that far. But luckily for us, we're thrown a bit of a bone in terms of luck, which is that there's a horrible word that I still hate, which is interferometry. And what that means is that within radio, it's fairly easy to build the equivalent of a big telescope by actually just putting two antennas the same distance apart. So instead of building a 60-metre telescope, big dish like the Green Bank, instead we can very roughly put two antennas 60 metres apart, join them up by some wire, do some very clever computation work, and still see the same kind of image, still look as far back. It's kind of like being able to choose between listening to music, for example, via a speaker or via two headphones. It's, you use the same kind of idea of combining different amounts of sound. In this case, it's light. So indeed, that's what we've done. I work with a radio telescope in the Netherlands called LOFAR, the Low Frequency Array. This is a map of all of our stations, and what we've done is we've placed 2,500 antennas, mainly in the Netherlands, which is where you can see the concentration there, but with stations across Western Europe. And that means that we've built a telescope the size of Western Europe, basically. And with a telescope that size, you really can look back that many billion years ago. And that's what LOFAR does. So we've been doing that for about 7 years now, actually. 8 years. Yeah, we've been switched on getting first light for about 8 years now, trying to gather enough data in order to make the very, very first detection of these very, very first stars. And we're not the only ones. It's been a very healthy and friendly competition with our colleagues in India, South Africa, United States and Australia. And we've all been looking for this signal for at least 5 years, and we haven't found it yet. So when I started my PhD, I was told that by the end of my PhD we'd have the detection. Still waiting. I told my PhD student that started on Monday that he'll definitely have a detection by the end of his PhD. So we will see. But it's a really hard experiment. We know the signal's there because we exist. We know there had to have been first stars. So why is it so hard to actually find them? Well, the problem, certainly with the current generation, and all of those telescopes I showed you are what we call pathfinders. They are the current generation of radio telescopes, which are finding the path for doing this kind of experiment. It's very, very hard to link up 2,500 antennas, get them all to look at the same part of the sky and really understand what's going on. So we're really finding our way. And actually we're not even trying to look for even this, which you're already underwhelmed by, because it's going to be so messy, we won't even be able to see the individual bubbles with the current generations. We'll instead be able to see hints of them. What we're doing at the minute is kind of trying to look for simply a statistical detection. So we will still be able to find out a lot about our early universe. For example, we'll be able to rule out the most exotic models where there was maybe 2 first stars and everything else was black holes. But the first generation is about establishing where to look in the sky. And I'll get on to why that's still important. So I've given this talk for, I don't know, like 8 years. And I've always had this kind of slide with these same 4 front runners on it. But in February this year, I got a phone call from The Guardian saying, "Oh, we've heard there's been a first detection." News to me. It was embargoed. And it turns out it was from a telescope that I'd never even bothered to put in my slides. And what they did was very, very clever. They have made what we think is one of the first detections of the effect of these first stars in a slightly different way to what I've described so far. Now, what they did was, instead of looking for these bubbles 400 million years after the Big Bang, they looked for, just as these first stars were forming, around 180 million years after the Big Bang, they looked at how they heated the hydrogen. So if we go back to our piece of paper in our lighter where we're burning holes in it, there's that moment where you burn it and you can just see it start to heat. It doesn't quite burn through. So they were looking at that part before the bubbles. And quite fascinatingly, they did it with one antenna. They did it with a table in a desert in Western Australia. So it's a very, very simple metal table. Can you tell I'm bitter? I don't know. It's incredibly cheap. Like, I think they did this off their spare money, basically, from the university. And I mean, it's a very, very clever thing to do, and it's complementary, which is why I'm not completely bitter, because this is a very early thing. What they can't do with this is push further on. They can't push into the era of the reionization of hydrogen, as we call it. They can't determine, for example, what were the first stars, where were the first black holes, where were these bubbles, etc. And a lot of the kind of the finer astrophysics of it. But as a first detection, this is incredibly exciting, because not only have we had our first data point in this time, which is a relief after so many years. Oh yeah, that's just me saying what they were seeing. But actually it was completely unexpected what they found. So it wasn't just that they found it, it's that they found something incredible. And so as I've said, what they did was they, instead of looking for the bubbles, they measured the temperature of the hydrogen. So you've got temperature here, you've got the age of the universe, and what they saw was, as expected, the hydrogen was heated. So the first stars start to come alive, start to fuse, they just start to heat up all of this hydrogen. And then over here, you'll start to see it burn away the hydrogen in the stuff I've talked about so far. All is expected, except that the universe, the temperature that they measured was about doubly as cold as it should have been. So they should have started reading here about where this red line is. So what on earth is happening here? Why is the universe twice as cold as it should be? Well, the hydrogen is twice as cold as it should be. That might not seem like a big deal, except that when we took this data and we compared it with every single one of our theories about the first stars and how they would heat the universe, it didn't fit with a single one. So not a single one of our theories currently holds water, which is the most exciting thing that can actually happen in science, and I genuinely mean that. So what's happening? Well, I wish I could say that I have the answer. So how many months are we on now? 6, 7, 8 months on from this first detection being released. And it's still the main topic of conversation, as of course it would be. And we don't really know what can cause it. Now, when you want to make something colder in the universe, what you do is you collide it with something. That's really the only way you can make a gas like hydrogen colder in the early universe. So it's just like if you're going for a nice jog, you're full of energy, you're really, really warm, and then suddenly you crash into a tree and you lose all of your energy and you get a lot colder very quickly. So we know that something in the universe is bumping into the hydrogen. But what is it? There's nothing in the early universe that wasn't already in our equations, except dark matter, which I don't have time to go into because it's a talk in itself, but you'll have to take my word that dark matter is one of the largest outstanding problems in cosmology. We found out many, many decades ago that everything we can see, everything we understand, constitutes about 4% of our universe, and we are still looking for all of the rest. Forget dark energy, that's a completely different week, but dark matter, that's still 22% of the universe that we have never detected. And we have never detected this mysterious stuff. We can see its effect, but we've never detected it because it's famous for not interacting with stuff. And yet, the only way we can think of calming these hydrogen atoms down is if there's a large lump of dark matter in the way for it to just bump into. So if this is true, and I say if this detection stands up, then not only have we found the first stars, but we found another way of detecting dark matter, or seeing the effects of dark matter at least. And the fact is that dark matter itself, our understanding of that takes a whole paradigm shift as well, because we didn't think it should be able to do this. So within our first ever detection, I like to think of it as, I used to love Egyptology as a kid, and I always remember Howard Carter saying that, he chipped away that first hole into Tutankhamun's tomb, and he held up a candle, and all he saw is gold. And that's what it definitely feels like in my field, is, we've had a very crude first detection with a table in a desert. We've taken one temperature, a few temperatures, and what we found is something incredible that we never expected, that has far-reaching implications, not just for our field of wanting to complete our knowledge, but much further into cosmology about understanding our universe as well. Now I'm saying if, because incredible results require incredible evidence. And this is one experiment which took a certain number of readings, but we absolutely need more confirmation. So we need multiple experiments to confirm this data. We need multiple telescopes to observe the same temperature drop for us to believe all of the different mathematics and calibration and mess that goes into radio interferometry, and to really be absolutely confident that what we're seeing is that real drop in temperature. And hopefully within the next year we'll see that happening. There's been a lot of money thrown at this at the minute, as you can imagine. I'm hoping that within the next year, I've heard one rumour at a conference a few weeks ago that another telescope has detected something at the same time in the universe, but that's all they'll say, whether it's the same thing or not, but hopefully we should hear quite soon. So why is this so hard? Why? Why have we been searching for 8 years, and even the first detection, we can get excited, but we can't quite let ourselves go yet? It's because, you know, I've said that it's quite easy to build a gigantic telescope, but it turns out that a really, really gigantic telescope picks up everything else in the universe than you're looking for. And the universe is really, 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 really loud, especially when you're looking for something so far away that everything else in front of it just covers it up. So you've got all of the radiation, all of the light from every other galaxy in the universe. You've got the very, very loud radiation from our own galaxy. It's like trying to talk to your friend on the mobile phone when you're walking past a pneumatic drill right next to you. And remember, we don't even know what this signal looks like particularly. We can roughly guess it looks a bit bubbly here and a bit bubbly there. But in terms of knowing what we're looking for, it's a cliche, but needle in the haystack. Getting even closer, you've got electromagnetic interference from planes going overhead. We can detect, well, planes that we shouldn't be able to detect, actually, with radio telescopes very, very easily. The Netherlands, in particular, is a nightmare for windmills. And the arguments we have with people wanting to build windmills right next door to the telescope. We have cow interference because the Netherlands has a huge agricultural plain, and we have electric fences stopping the cows from getting into our telescope. And of course, electric fences produce electromagnetic materials interference. And of course, we have radio, which does indeed, radio interference is coming in at the same frequencies that we're detecting. And so we have to just chuck away all of our radio data at the frequencies that, well, Chris Evans and everybody else is producing at. Now, my personal job is to remove this stuff, which is hard, which is why I have a job, but it's manageable in that it looks very different to the signal we expect statistically. So I'm not going to go into how particularly, but it's kind of like trying to listen to the radio, trying to listen to classic FM, for example, at the same time as trying to listen to a heavy metal radio station, which I wouldn't know the name of. And you can, even though you don't know what the signals are, you don't know what the individual songs are, you can kind of intuitively understand how to separate them out. And so with some very hard statistical methods, this is at least salvageable, let's say, though it's very tricky. This stuff, however, is a lot harder to deal with, in a way, because at the minute we just have to chuck it all away. And so we've talked about the pathfinders, we've talked about what we're doing now, we've talked about how we try and keep these cows out of our telescope. An obvious conclusion is that maybe we just need to go somewhere a little bit quieter. And that's what we are going to do. So I want to talk a little bit about the next generation. And the next telescope that I'm heavily involved in building at the minute is called the Square Kilometre Array. And what we're doing is we're going to be building a radio telescope in the Western Australian desert. Now, this is a plot of land around the size of, I think it's about 2/3 the size of England, I think it is, with a population of 113, 29 buildings, and about 3,000 cows, unpenned, so it's okay. And this is what we call a radio quiet environment. So we don't pick up too many radio signals, we don't see too many planes. We have polite notices asking the 114th person to wander into the desert to please turn off their mobile phone. And in terms of wildlife, it's a little calmer as well. So the Netherlands, we have an absolute nightmare in terms of mice chewing the cables, in terms of, we had a heart-stopping summer where a group of, was it otters, I think it was making its way down a river, getting ever so close to all of our cables, and we could do nothing except watch and hope that they didn't go anywhere near them. Luckily here, we do have to worry about the odd lizard nesting, but it's not so big a deal. The main problem we have actually is getting out there. It's I was just telling someone a minute ago that, you know, I went out there and I was told that this ground was right next to Perth. I got out there and it turned out to be a 4.5 hour drive. So if something does go wrong, it's a real pain to get to. Now, the Square Kilometre Array is going to consist of what we call Christmas tree antennas. As you can see, a jumble of them here. It's because they look a little bit like Christmas trees and because we all unashamedly have one in our office acting as a Christmas tree every year. And they are going to form stations across the Western Australian desert. And there's going to be so many of them that it really is going to look like the ground has measles. There's going to be 130,000 antennas in the first batch that we're starting to build next year. By the end of the, what decade are we? By the end of the 2020s, there'll be 1 million antennas based across Australia. And that kind of technological buy-in can build you a telescope that not just looks back 13 billion years, because we've already done that. It manages to really hone in on these bubbles. It manages to go from this to an incredibly clear picture over a massive area of sky, over several different areas of sky, to see how different areas of our universe evolved at different times. And we're going to be able to build up slices, images from these different times in our universe and watch our universe evolve. So it's not even that we're just going to be able to... Is this running? Yeah. It's not even that we're going to be able to simply see a static picture of a bubble and try and understand what's going on from that, but we'll be able to see these bubbles expanding and evolving and merging until the universe is one giant white, it's white here for ionised hydrogen, into one entire ionised universe. So we'll have a home movie of our universe over around 1 billion years that we'll be able to download and watch. So this is no extrapolation, particularly. This is actually having a home movie of the ancient Egyptians building a pyramid, and we'll be able to understand how they did it. So in terms of our alien Andromeda, it's like him finding a birth video and suddenly realising he didn't come from a stork at all. Suddenly he has a complete data set. And suddenly we can actually understand what started our universe. And not only that, but if this edges is the table in the desert, if this edges data is true, then we've got something thrown in for free. We can actually see the dark matter. So this is the dark matter web within the universe, and we'll be able to really extract cosmology from this movie, as it were. Because the way these bubbles are created, it will mean that we can understand what the dark matter was doing. We'll be able to extract the completely unseen dimension of our universe, as it were. Which is worth doing, I think, for the sake of a few antennas in the desert. Now, the Square Kilometre Array is a huge international effort. It's actually very cheap. It's only about 650 million euros, which is nothing compared to the billions that the US have spent on the JWST, which is the optical telescope. So people are quite keen to invest in this current climate, because it means they can still get to look smart, but for less money. The UK is one of the main partners, and the headquarters is actually based in Manchester, which is rather bizarre considering it's being built in Australia and South Africa, but not complaining. So if you ever head up to Jodrell Bank, you can go visit the SKA headquarters. And it's something the UK government invested in very early on. It's rather unheard of that they actually pledged money before the deadline by several years, because they were so keen to be seen as one of the main partners. And that's not just because David Willits was very interested in the first stars. It's because, as a technology, this Square Kilometre Array is absolutely incredible. It's worth investing in. Because if you consider how much data it takes you to, say, download an episode off iPlayer, you can be watching it download, you've got to be careful of your data plan, etc. We're downloading what is the equivalent of a home movie of 1 billion years long. That amount of data is huge. We're doing petabytes per night, which is what, here we go, 35,000 DVDs every second of data. And we simply actually don't have the technology to handle that right now, even though we're building it next year. we don't have enough hard drives in the world to be able to store all of this raw data from the early universe. The fibre optic cables travelling from our telescope to me via broadband, for example, cannot cope with this kind of data. So at the minute we're having to chuck it away. That's our current plan, is to chuck a whole load away. And so the UK government, every other government that's involved actually, is interested because we are driving the technology change in terms of we are working with NVIDIA, for example, to develop better cooling chips, because our data flow is the biggest in the world, or will be the biggest in the world. And so we are their test ground. We're working, to try and find different ways of transferring data. It's all about big data, which is a big flash word. But the SKA is the big data project at the minute. And it's got to the point where, in terms of data transfer, we simply don't have these fibre optic cables to transfer it now. And we're starting next year, so we're having to start looking at solutions such as the Amazon Snowmobile, which is a gigantic HGV, which is stuffed full of hard drives. And the current plan is to drive it into the desert, download a whole load of data, drive it to the airport in Perth, and then ship it to people like me via FedEx. I'm serious. 650 million euros, it buys you a truck. It's great. And this is actually why I really love what I do. I love radio astronomy, because going into it, you can be quite underwhelmed by a picture of red with some white bubbles on. We're basically sticking some metal in a desert, and this isn't special metal. This is just metal. These cost, I've got one in my office across the way, and it cost me 30 euros to buy one of these. They're very, very cheap. And you just stick them in a desert, and you hope that somebody turns their mobile phone off, and you hope that a kangaroo doesn't push it over. There's no clean rooms. There's no fancy rocket launchers. There's no gyroscopes going wrong on the Hubble Space Telescope and fancy drones going up into space to fix it. There's just a lot of down-to-earth grittiness. But at the same time, we're using this kind of technology to do some of the most incredible science that, in my opinion, has ever been done, because we are looking back right to our origins and not just extrapolating, but watching this stuff happen. I think I'll leave it there. Thank you.
Thank you very much, Emma, for that very exciting explanation of where you are now. You'll have to come back. Is it next year or the year after?
Or in 10 years,
Well,
whenever it happens.
Whenever it happens. Whenever you see it.
Yeah.
Well, thank you very much for that.